We come to the final topic in this chapter of simulation, and really the culminating topic, as you can see from the chapter title, Simulating Battery Packs, is really what we've been building up to all along. We've reviewed two different models of battery cell dynamics, one of them, of course, the equivalent circuit model, and the other the physics-based model. And we can use either one of those to simulate cells. To do so, we just evaluate the model equations once per sample interval, and we update the state of the model and we update the output of the model once every interval. The question that we address here is how to simulate battery packs. And packs comprise cells in series and in parallel. So what changes are required to do it? And sometimes the changes are simple, sometimes that may not be quite so obvious. But by the end of the section, you'll see how to do it, and it will not be that bad. First, we consider what happens if we have cells connected in series. So I have a battery cell, and then another battery cell, etc. And by Kirchhoff's current law, we have to have, if I've got current going through this stack of cells, then each cell must experience the same current. Now, if all of the cells happen to have exactly the same initial state and identical parameters, then in fact, over time, the cells would have exactly the same state and voltage as well. And we would need to simulate only one cell because all of the cells would be identical. If they start at the same place and they have the same dynamics, then they're going to be identical. But this is not generally true. For various reasons that we'll think about a little bit more in Chapter 5 when we talk about cell balancing, cells don't generally start in exactly the same state. And furthermore, cells don't generally have exactly the same parameter values either. Even at beginning of life, as the cells roll off the production line, there's some manufacturing variability, and then over time the aging of the battery cells tends to cause them to their parameter values to diverge from one another rather than to converge. And that's mostly because of thermal variation in the battery pack, that some cells will age more quickly than others. So, we're going to have to do something else if we want to have a good description of the simulation of a battery pack. We in fact have to simulate all of the cell's dynamics independently. So each cell will have its own state that we maintain in our simulator and model parameters that we maintain in our simulator. And then we update all of the states and voltages, etc. every sample interval. When we're looking at a series-connected set of cells, we might also consider the fact that there's interconnections between the cells, and there can be fairly significant resistance there. The overall series resistance of a high-quality battery cell for automotive application is in the order of a milliohm or so, and the interconnect resistance of the tab or the terminal of the cell connected to some wiring and connected to the next cell terminal, that can also be on the order of a milliohm, probably about a tenth of that, but it's certainly significant when we're considering the entire resistance of the battery pack. So the voltage of the battery pack is the sum of all of the cell voltages, Ns being the number of cells in series, minus Ns times an interconnect resistance times I. And this interconnect resistance we could think of 2 times a tab resistance, where a tab is one of the terminals of the cell, plus whatever wiring is in between it. So either way, we could think about it either as the total interconnection resistance between between two cells, or the tab resistance of one cell. When I connect cells in parallel, we can increase the current carrying capacity, for example. So connecting in series increases the overall voltage, and parallel increases the current. So we very often have series-connected packs for low-energy, high-power applications like HEV. But for high energy, I also need to get high current, and we often have cells or even entire sub-packs that are connected in parallel. And in Chapter 1, we previewed this idea of building up a battery pack in a modular approach by putting cells in parallel to make a module or putting cells in series to make a module. Usually we do a bit of both, but here we look at the two extreme cases. What happens if we make modules by putting all of the cells in parallel inside a module? That's PCM, which is parallel cell module. And what happens if we make modules by putting all the cells in series to make a module? And that's SCM, or series cell modules. So this is PCM and that's SCM. And this configuration is 3 cells in parallel, 96 cells in series, so it's the overall battery pack size of a Gen 1 Chevy Volt. The Gen 2 Chevy Volt was recently announced and it has a different configuration. They do modules differently from this, but this is the total number of battery cells, so we might use this as being somewhat indicative of an actual battery pack in an actual vehicle. So if cells differ, we need to simulate the cells individually. But how do we simulate the cells individually is a question we hope to address here. Because the cells differ, the cell currents will be different, and that will update the states differently. And how do I actually compute what the different cell currents happen to be? We're going to first consider the PCM approach. And so in the PCM approach, which is drawn here, we have one module has a bunch of cells in parallel, the next module has other cells in parallel. We're going to look at one module only right now. So I have a battery pack current going through here. Somehow it's split up among all of the cells in the module, but by the time I get to this point right here, it has exactly the same current. Just by Kirchhoff's current law, I can't have differing currents going through. So every PCM is going to experience the same pack current as every other PCM, but how that pack current gets split up and distributed among the cells of the PCM depends on the parameters of every individual cell. So we're going to look at one PCM. So there's one. So looking at one PCM, we reuse some of the ideas that we saw in the last topic of notes when we were looking at constant power and constant voltage simulation to remember that our cell model has a voltage that has a fixed part, which is drawn as this voltage source here, and a variable part, which is drawn as the resistor here. Now this is not OCV, this is OCV plus the fixed part of the hysteresis for this time sample plus the, actually minus really, but the contribution due to diffusion, which depends on the present state, which depends on the past input current. So all of this is the fixed. This is what we called VF before. We have a slightly different name for it now. And then we have this resistor. Now, in the PCM, in one PCM, we have a whole bunch of fixed voltage sources and a whole bunch of resistances, all wired as shown, with a voltage source and a resistance in series, and then parallel branches of all of these. We can use standard circuit analysis tools to analyze that circuit to figure out what is the current split. Basically, this is a current divider with a slight modification because of the voltage sources in each branch, but it's essentially a current divider that divides the pack current up into individual branch currents depending on the branch resistances and the branch voltages. So to do this analysis, we remember Kirchhoff's voltage law. Kirchhoff's voltage law says things in parallel have the same voltage. So everywhere on that bus has the same voltage. Everywhere on that bus has a different but the same as each other voltage. By Kirchhoff's current law, the sum of the branch currents must equal the total battery pack current. So we define the current through branch J to be IJK. So this is I sub 2 comma K. If this is branch 1, branch 2, and this is branch NP, because I've got NP things in parallel. And the fixed voltage of this branch here is going to be V1K, because that's branch 1. Now before we called it VF, but here it's just V1 for that branch. The overall PCM voltage we'll call VK, and the resistance of the jth branch is R0J. So this is R0, 1, because that's branch 1, and this would be R0, 2, because it's the second branch. Then the current through the resistance in a certain branch is equal to the voltage drop across the resistance divided by the resistance. This is Ohm's law, so delta V over R. The voltage drop over a resistance in any particular branch is going to be Vj, the voltage of the fixed voltage, minus the voltage of the overall PCM, and the resistance is R0. And the signs are arranged in such a way that our sign convention is maintained, that in order to charge I will have a negative current, in order to discharge I'll have a positive current. We then do that for every one of the branches, so we get an equation for every branch for the current flowing through it. And we arrive at a total, not a battery pack, sorry, but this would be a PCM current, which is actually the same as the battery pack current because the same current goes through the PCM. So never mind, it was correct. Misleading maybe, but correct. That the pack current is equal to the sum of all the branch currents. So it's the current through branch 1, through branch 2, all the way up to branch NP summed together. Now usually our simulations are run such that the pack current is the input to the simulation, and then I have to figure out everything else as the output. So this is going to be an input. This is known, that's known, that's known, that's known, that's known, that's known. The thing that is unknown is what is the PCM voltage. And there's a lot of them on the right-hand side, but I can rearrange this expression in order to actually solve for the battery pack current. So I would do so by rewriting this as this is V1K plus V over R01 plus V2K over R02 plus V3K over R03 dot dot dot, and then minus VK over R01 minus VK over R02 dot dot dot. And I would combine all of these together and all of that together. This I move over to one side. This I combine together and multiply and divide both sides as appropriate to solve for VK. So a couple lines of algebra I will let you do. The rearranging gives us this here. So the PCM voltage VK is equal to all of this stuff here, well, all of that stuff, and then minus IK, which is this sum, and then divided by the normalizing factor over on that side right there. All of the terms in this equation are known. I is the input, the fixed voltages are known, the resistances are known, so we can solve for VK, and then once I solve for VK, I can go back to this equation here and solve for all of the branch currents. And once I solve for a branch current, I know the current going through every one of the cells, and I can update the state of every cell. So the process is, first find the PCM voltage based on pack current. Second, find all of the branch currents inside of the PCM. Third, update every cell state inside of the PCM, and then repeat. So that is the PCM. Now SCM is done a little differently, but the same principles apply. In a series connected module, again, I've got a cell, and the cell is going to have a variable part and a fixed part. And then I've got another cell with its variable part and fixed part. And then I've got another cell with its variable part and fixed part, etc. And then that is one SCM, and then I put a bunch of SCMs together in parallel. A single SCM like this I can collapse using just linear circuit analysis techniques into an equivalent circuit, and the equivalent circuit looks like this. This resistance here is the sum of the individual resistances. It's that resistance plus that resistance plus that resistance. This voltage is the sum of the voltages, so that fixed voltage plus that fixed voltage plus that fixed voltage, etc. So all of the cells have been collapsed into a single equivalent cell with a high resistance and a high voltage, basically the sum of the resistances and the sum of the voltages. So in this diagram, it looks like a PCM. In fact, that there is SCM number 1, that there is SCM number 2, etc. This is SCM number NP. So each one of these is a high voltage thing instead of a low voltage single cell. But because it looks just like a PCM, the equations end up being pretty similar when we're simulating it. So the lumped voltage, the lumped fixed voltage of an SCM we'll call VJK. So this is V1K. And the lumped resistance, that we're going to call R01, and so forth. But now these are of the entire SCM, not of just one cell. Using exactly the same equations as before, we get a voltage. This is not a cell voltage or a PCM voltage, but instead it's the bus voltage of the SCM, of all the SCMs in parallel. So that there is, the difference between those voltages is the bus voltage. And the equation is exactly the same, but different interpretation from before, because these are lumped resistances and lumped voltages in here. But because of that, I know the pack current. I solve for the bus voltage. Once I have the bus voltage, I solve for the SCM currents, just as before. And now that I have the currents through each SCM, the same current, by the way, goes through all of these. I have current going through there. The same current goes through every cell in an SCM. And I can compute updates to all of the cell models using that value of input current. There is some code in an appendix for simulating a PCM, and we look at some results from simulating that code here. Again, you should be able to copy the code into MATLAB and run it. In this example, I've got two cells in series and 3 cells in parallel. And I'm running the battery pack. In fact, looks like I'm lying because I show results for 3, so I must have used 3 and 3. In the simulation, the cell states of charge are randomly initialized between 30% and 70%. That would not be typical in an application. Usually they'd be much closer together than that, but here I just want to be able to demonstrate some of the features of a PCM by saying, suppose somehow this pack was very unbalanced at the beginning of simulation, then what happens? The resistance values are randomly initialized between 5 milliohms and 25 milliohms. Cell capacities initialized between 4.5 amp hours and 5.5 amp hours. So there's a lot of variability in the initial state and the parameter values of the pack. We repeatedly discharge and charge the battery pack. We discharge until the lowest SOC in the pack hits 5% SOC, and then we charge until the highest cell hits 95% SOC. We repeat that over and over again with a constant current type of simulation. And then after 45 minutes, we allow the pack to rest and see what happens, both during the forced behaviors and the resting behaviors. And the plots show some results here. So I've got 3 PCMs, 3 in series, and then each PCM has 3 cells inside of it, so 3 in parallel. And the wiring configuration looks like 3 things, 3 things, 3 things, and then that's it. So that we have actually a real PCM architecture. In PCM number 1, the top left plot, we see the initial states of charge are quite random, as expected. I've got a red line, a blue line, and a green line showing the PCMs, the different cells. And blue is cell 1, green is cell 2, red is cell 3. Not that it matters because they're really indistinguishable in practice. The green line has a very wide variability in state of charge as I cycle the battery pack, so that leads us to believe that cell must have a very low capacity. In fact, it's the widest range of state of charge, so it must have the lowest capacity of all the cells in the battery pack. The red line has much less variability, the blue line has even less, so they have a higher capacity. We see that the states of charge of the cells in PCM number 1 are converging toward each other, especially during the rest interval. They tend to converge towards each other. Well, that's because the cells are in parallel, and if I'm not forcing different current through the branches, the voltage across all the cells has to be exactly the same, and that will tend to happen as all the same cells have the same state of charge. Now, the reason these don't converge to exactly the same state of charge in this rest is because of hysteresis. Hysteresis really kind of messes us up. We end up in very different hysteresis states, and the hysteresis state does not change as the cells rest. So hysteresis voltage doesn't change. The capacitor voltage can change in the diffusion model, and the open circuit voltage can change, but the hysteresis voltage cannot. And so as the capacitor voltage decays to 0 and hysteresis voltage remains fixed at whatever value it was at time 45 minutes, the state of charge has to adapt over time in order to cause the overall terminal voltages of the cells to remain constant while this pack is resting. So it's very interesting. We see that there is some disparity in cell SOC even when the cells are hardwired in parallel and the pack is resting. Looking at the other PCMs, PCM number 2, there's much less variation here. The capacities of these cells appears to be much more similar to each other, but again we see that due to differences in hysteresis, the overall states of charge do not converge to the same value at the end of time, although eventually they will converge to constants in the different cells. PCM number 3, similar behavior again. And the bottom right plot shows the average state of charge for all the cells in each of the PCMs. So the blue line is the average of all 3 states of charge in PCM number 1. The green line is all in number 2, and the red line is all the cells in number 3. There we can see as the pack is charged and discharged, the averages go up and down, just like we'd hope. But when the pack is allowed to rest, the average state of charge in each one of these modules remains absolutely constant. Even though some individually are going up and some are going down, the average is constant. And furthermore, the state of charge of PCM number 1 is not converging to PCM number 2 and not converging to PCM number 3. There's no mechanism in this plot to move charge between, for example, PCM number 1 and 3 in order to balance them out so that they would get different, or so that the states of charge would become more similar to each other. That's why we're going to need balancing. And so again, we look at balancing in Chapter 5. And this simulator that we develop here is going to be used as a basis for evaluating balancing simulations in Chapter 5, so that we do then, in fact, move charge from one to the other, which will over time cause these states of charge to go down and this one to go up, and we can balance states of charge of these modules using different electronics and algorithms to do so. Also, as we run the simulation, we can get insight into the different other things like currents. Here we see the current of each individual cell in PCM number 1. Again, the green line was cell number 2, and that one had the lowest capacity, so it's actually seeing the greatest current, and it probably has a lower resistance too, although I don't know that for sure. But it's seeing much greater current than the other cells are. And notice that even when the pack is resting, the cells are not resting because the cells are connected in parallel to each other. So the forced current through the pack is 0, but the one cell is is discharging into another cell in order to maintain the constant voltage as the capacitor currents slowly change and go to zero, and as the open circuit voltages have to then change as well to maintain the overall constant voltage of each PCM. We saw the greatest variability in PCM number 1. PCM number 2, there's much less variability, and we see something that's far more indicative of a constant current charge and discharge cycle, so first discharge, then charge, and repeating as this battery pack operates. But there again is some variability because of the different capacities and resistances of the cells as to the current experienced by each one of the cells. PCM number 3 is also a little bit different. And then the maximum average SOC minus the minimum average SOC is a single line. In the previous plot we saw the average SOC for each PCM. Now we look at the maximum deviation, and we see that we go up to a maximum of around 14% SOC difference between cells. And if we want to keep the cells safe, then we need to be really careful. So the code to reproduce this example is in the appendix, and it should be fairly straightforward now that you've seen the equations. The only tricky part is how the data is stored in order to kind of compactly represent a lot of different cells in parallel and series with different parameters each. I'll let you have a look at that. This is PCM code that I've given, but to simulate SCM you have to make a few simple modifications to be able to implement the SCM equations instead of the PCM equations. It's not that hard to do. So where next? We have arrived at the end of chapter 2, where we have reviewed our cell models and we've looked at different ways of incorporating these models into simulations of cells for constant current, constant voltage, constant power, simulating the application of a vehicle, simulating battery packs all together. Our focus in this course is on applying the empirical models, the equivalent circuit models. We could do all of the same kind of things we've talked about in this chapter for physics-based models. The output equation of our physics model is a little more complicated, which makes things like constant power and constant voltage a little bit trickier, but honestly not that much worse. So we could do the same kinds of things for that model too. We've seen how to use the model, whichever model, to predict and simulate cell performance. Now we need to go back and remind ourselves what are the requirements of a battery management system. We go and we look at requirement 1, 2, 3. We've kind of looked at all of those. Requirement 4 of the battery management system had to do with estimating the state of charge of the battery cells, estimating the internal state basically of a battery cell. Well, there's a lot of ways of doing that, but all of the best ways of doing that are somehow derived from a model of cell behavior, so hence the focus in this chapter of reviewing the models. But in the next chapter, in chapter 3, we spend a lot of time really going pretty deep into model-based estimation to estimate the internal state of the cell, and maybe the biggest highlight out of this is an estimate of state of charge of this cell, which we'll call Z hat. So let's move on. Let's begin to look at state estimation for a battery cell using the models that we've developed.